This is the Earth Science Classroom. Welcome back to the channel. This video is all about silicate minerals. It is a additional video in the minerals playlist looking at a certain kind or certain group of minerals in particular, which is silicate. And this video is going to discuss what they are, what is a tetrahedron, how they form, and also different types of minerals that are classified in the silicate group. So there's different types, and we'll discuss them in this video. Alright, so what are they? So these are a group or class of minerals. Now, as mentioned in the previous video, there are over 5,000 known minerals. And there are pretty much 7 major groups that we distinguish all these minerals into groups based on their chemistry and their different characteristics. So the one group we're looking at in particular obviously is silicates. And within silicates as a group, there are 27 different types of silicate groups and over 1,100 different silicate minerals spread over these 27 groups. So as you can imagine, this is the biggest group and the most important kind of, really, you could say it, most important group of minerals that a student should know when studying minerals and mineralogy. And also it has a vast range of rock forming minerals contained in silicates. So if you're looking at the rock cycle and petrology and going forward in different types of rocks, you are going to discuss silicate minerals in great detail. So looking at chemistry of these silicate minerals, by definition, they must contain silica or silicon, okay, oxygen. Now, in terms of the different arrays, now quartz, which is the purely SiO2 or in a form of SiO4, which is the tetrahedron shape with the 4 oxygens, which we'll get onto in a second, or you have, this is the one type of silicate mineral, as I mentioned before. There's loads more, and they generally like to add on to the chemical formula a lot more different types of elements. And when you add the elements into that SiO2 or SiO4 base, let's call this a base, right? The foundation of silicate minerals, you can have a wide variety of minerals created when you just add in different elements, such as iron, magnesium, potassium, calcium, and sodium. Again, these, as I mentioned earlier in different videos, these are also high percentage elements found in the crust. So these are common. And as oxygen, as an element, is extremely, let's say, sticky. It's a good way to describe it. Very sticky. It's going to bond with all these different elements in different amounts and different structures and degrees along the different bonding sites. You get all these different elements, different minerals created under the silicate mineral banner. So what you end up with is silica plus oxygen as elements equal combined 72.2% of the crust. So the majority of the crustal elements that we find naturally occurring are silica and oxygen. And silicate minerals in general that contain the Si and O in the chemical formula or composition equal 92% of the crust. So there's 8% left, which are called non-silicates. Now, these are groups of minerals that do not have a combination of SiO2 or SiO4. Okay, they might have an SO4 or an S, or they might have a an oxide, okay, just a simple oxygen, but they don't have the SiO2 or SiO4 combination. So these non-silicate minerals do make up a portion, but only 8% of the crust, and some are rock-forming minerals, and I'll do a different video on that as well, but today we're going to concentrate on silicates. All right. Now, I mentioned a base for all silicate minerals, which is the SiO2 or the SiO4. Now, this one's more common in terms of the structure. And don't forget, a mineral needs a certain structure which is solid, inorganic, naturally occurring, and that structure will contain the chemical composition, which is the elements, in a certain arranged order and repeating pattern to create a certain structure that is consistent with each mineral. So SiO2, SiO4, this one here is our tetrahedron. All right, so it looks like this. So you're going to have silica, that element, or the atom, right, in the middle. And what you're going to have is a three-dimensional, like basically a pyramid shape. Okay, so you're going to have, I'll use purple for oxygen. So you have the oxygen, the oxygen, the oxygen, and oxygen. So there is, 4 oxygen. So I'm going to put oxygen times 4. So that's the O4 right there. Okay, and the singular silicon, right, or times 1 there. So there's our 1 silica. Right, so all you do is you draw in the bonds. I'll use red. All right, so we got that. Well, so you have this three-dimensional shape with silica atom in the center, and you have these exterior oxygens kind of creating that shape, and the silica in the middle organizing that and kind of like dictating it, but the oxygens on the outside. So. And oxygens are usually a larger atom as well. So you get this shape, this nice base. And what you have is you have the chemical bonding with the electrons. And the other oxygens will bond like this. And you'll have, obviously, the sticky oxygen and the electrons. They will gladly share, and you'll get this structure and this repeating pattern of bonding silica or even quartz silica structures like this in repeating patterns. Now, this tetrahedron is found in single pairs and is the basis to start a chain. And when you get the chains, you start to form these different structures and different kinds of shapes that are all made up of the silica and oxygen and, as I mentioned before, the other added elements like magnesium, like iron, like sodium, and they will form their own different shapes, which is kind of cool. So these are formed through, obviously, magma or lava. Now, again, chicken or the egg. The Earth was, when the Earth was formed, was a very proto-Earth, 4.6 to 4.3 billion years ago. It was kind of like this brand new molten ball accumulating by gravity and mass, and it's extremely hot, and everything was magma and liquid rock. So you can argue that all these minerals, even the zircon minerals, which is a silicate mineral, a zircon mineral, which is, I think, by researchers, the oldest form of mineral and also rock, which was found in Western Australia and certain parts of Canada and the Laurentian Shield. up there and the Hudson Bay, they're the oldest rocks, dating back to about 4.3 billion years ago. So these are the first rocks, really, first minerals and rocks that really crystallized out of the magma as it started to cool. And when it cools, it consolidates, and it has a phase change where you start to add the bonds between the atoms and the elements and the minerals. They start to bond and form, and these minerals start to crystallize. So when you hear crystal and crystallize, think the mineral starts to take shape. The mineral starts to grow as a solid material and matter from a liquid origin or liquid state. And these zircon minerals are the oldest in the world currently. We may find older ones, but based on how the Earth began, I think this is probably the oldest we can find. And then obviously we know that minerals can either form into rock as themselves or combine to form a variety of rocks with a variety of minerals. For example, like granite has 5 main minerals inside of it. So again, these rocks are these minerals are the building blocks of rocks, which we'll get onto in different videos. So there are different types of silicate minerals. As mentioned before, there are 27 classes of silicate minerals, and in total there are over 1,100 known minerals in the silicate group, which are broken down into these classes. Now these classes are defined or characterized by the structure, the varying structure that these minerals can come in, and also the level of bonding, which again denotes the structure and the shape. So the shape and the form, or what we call the crystal habit is another word for shape, can change based on the style and shape or the amount of bonding of that silicate mineral. Obviously, generally, the more simpler the formula, the more straightforward the shape. You get more additions of or add-in of chemicals or elements onto that base SiO4. You might have more complicated shapes. So start with your basic pyramid, right? Your three-dimensional shape, your 3D shape. You have the Si in the middle and the O, oxygen, oxygen, oxygen. Okay? It's 4 on the outside, 1 in the middle. Okay, so as you can see here, there are six main structural groups or patterns that the SiO4 tetrahedron can form into based on the amount of bonding through the oxygens. The silica really is just in there to control the tetrahedra and join with the original oxygens, but then the oxygens on the outside can join with other silica elements as well to form different patterns. So these patterns are repeating and they form different shapes, different habits. So let's take the first one. Okay, so orthosilicate. Now I made it capital, the first part, to change, to make it more obvious. Orthosilica or nesosilicate. Now these are very dense, very densely packed silicate minerals, and they are basically, you have your pyramid, all right, there, and you have your silica in there, okay, and basically they're going to form on the edge like this and be very tight, forming like a nice joined sphere, okay? And it's very, very dense and a strong mineral. So that will be your topaz as an example, be your zircon as an example. All right, and these are usually isolated single short, small chains of repeating silica on using the one oxygen right here and going around in a circle type shape. Next is your phyllosilicate right here. Okay, these are your sheet minerals or silicate minerals. Now, think of a sheet as a single layer of SiO4, and basically they are very thin. Okay, extremely easy with cleavage. Okay, obvious cleavage through one plane. So they can break through that natural area of weakness between the bonding, and these sheets go in very large, flat patterns of the repeating triangle. So large and flat. They repeat down and all the way through. Okay, and they can also repeat this way, but very flat and wide, creating our classic muscovite micas or micas. All right, and also looking at some clays are in this, like kernite, as well as the classic sheet phyllosilicate minerals. Next, the inosilicates, all right, or your chains. You can have a single chain or you can have a double chain based on how many oxygens are taken up. So you have your chain like this. I don't want to do it 3D. I'll just show you there. Have your single chain like this, where they join up using one oxygen, and this is a single chain. And in some cases, to make it a double chain, I'll just add it in different colors. So it'll be like this. All right, and this, and this, and that. So you'd have this double chain where on certain tetrahedra, you have bonding right here, creating a double chain, but there's also a lot of space in between. So single to double, and that is your inosilicates. And a good example of this is your pyroxene, and some of your amphiboles, and your hornblende. Next is cyclosilicates. These are your ring silicates, again, making a larger ring system. So similar to ortho, but a lot larger in number. And they usually come in six-fold. And a good example of this is tourmaline or tourmaline. All right. Your tectosilicates, these are our three-dimensional framework. And basically, these are our feldspar group. So plagioclase, all different types. Again, you can add in the sodium, calcium. This links up to, again, big part of the Bowen's reaction series. We're going to have the continuous and discontinuous series of reactions based on the additions of elements and what temperature it's going to cool at. So the feldspar group is our tecto three-dimensional framework minerals. Last is our sorosilicates, or also called pyrosilicates or disilicates. Now these are our basically octahedral chains. Now these chains, again, multiple patterns repeating, but octa means 6 atoms in chemistry. So what we're looking at is you have your silica, you have your oxygens, right? And you also have 2 more oxygens on the side. So you have your silica base tetrahedron, right? Tetra meaning 4, and then you have this extra 2 oxygens added onto the silica, making a larger atom. So this is our octahedral chains, and this is our sorosilicates type, and these are the 6 groups or 6 types of shapes we get by obviously starting with our nice base, silica, SiO4, and then adding on different ways, whether it's one oxygen, adding on to other ones, or it's 2 making a 3-dimensional, or it's tight, which is more ortho, so we can get different patterns, and that would change different types of minerals we get in our silicate groups. All right, thanks everyone for watching. Hope this helped, and see you in the next video.